Hi everyone. In this section on torque and rotational motion, I'll begin with an introduction to angular quantities. A rigid body is an object of definite size and shape. The particles within the rigid body have a constant relative position to one another. Previously, we've looked at objects like this and their translational motion by considering the motion of the center of mass. We know from Newton's second law that a non-zero net force acting on an object will cause an acceleration of its center of mass. In this section, we'll now look at rotational motion of rigid bodies. Objects can either undergo rotational motion, translational motion, or both at the same time. In this section, we'll consider purely rotational motion. Let's begin with this image depicting three types of motion of a rigid body. First, here we have translational motion, which is when the object moves as a whole, but does not rotate. Then we have rotational motion, where the object rotates about a fixed axis. In this case, every point on the object moves in a circle. Lastly, we can have both types of these motions occurring at the same time, which is combination motion. So this is where an object rotates as it also moves along a trajectory. And there's an example here of a parabolic trajectory while an object is rotating. So again, in this module, we will focus on this case, which is purely rotational motion. Now let's consider an object that is rotating about a fixed axis of rotation. To specify the location of a point on the object, such as point P here, its angular position is used. Theta is the symbol used for angular position, and this is measured counterclockwise from a zero reference line, which is shown in this diagram here. Generally, for angular quantities, radians are used instead of degrees, and you can convert between radians and degrees by using this relationship where pi radians equals 180 degrees. Note that r here is the radial distance from a point on the body to the axis of rotation. So it's the radius of the circle that this point on the body makes as the object rotates. A particle moving around a circle of fixed radius r travels a distance called the arc length as it moves through an angular displacement around the circle. So I have some definitions here. Angular displacement is the difference between an object's final and initial angular positions. It's represented by delta theta. We have final angular position minus initial angular position. Then the arc length in meters is defined as L equals R delta theta. We can see that if a particle travels around the whole circle, then it travels a distance of L, the arc length, equals R. 2 pi, it moves through an angular displacement of 2 pi radians, or 360 degrees in one full circle, which gives 2 pi r, and you'll notice that this is just the circumference of the circle. Now let's look at angular velocity. Recall from circular motion that the speed of a point on the object as it rotates in a circle of radius r is the circumference divided by the time required for one cycle of the motion, or the period. So we had v equals 2 pi r over the period, which gives a speed in meters per second. For an object moving at a constant speed, the formula gives that constant speed, but if the object is accelerating, then it will give the average speed. Similarly, we can define the average angular velocity, omega average. Omega is the symbol for angular velocity. It's defined as v over r. So if we plug in this relationship for speed here, we get 2 pi over the period for the average angular velocity, omega. And the units of angular velocity are radians per second. Note that the average angular velocity is the rate of change of the angular displacement of a particle per unit time. So we can define this similarly to linear velocity as delta theta, the angular displacement, over delta t. Just a few more notes on angular velocity here. All points on a rigid body will rotate with the same angular velocity. Now note that this is not true for linear velocity. Since different points on the object are at different radii, They each travel a different distance or circumference in one period, which means that points at different radii would travel at different linear speeds, though the entire object rotates as one, meaning that the angular velocity, which gives in a sense a measure of the rotation rate, is constant. Also note that we can also define instantaneous angular velocity for an object that is accelerating while rotating. That would just be omega without the average label. And as we've seen previously, with linear quantities, this gives its value at one particular instant in time. Angular velocity is also commonly measured in revolutions per second, where one revolution is equivalent to 2 pi radians. So 1 revolution per second equals 2 pi radians per second. Or you'll also see the unit of RPM, and this is revolutions or rotations per minute. So 1 rotation per minute, 1 RPM, or 1 revolution per minute is 2 pi radians over 60 seconds, which make up 1 minute. Angular velocity is a vector that points along the axis of rotation. So as with all vectors, there's a sign convention that goes along with its direction. So the sign convention for angular velocity is that it's defined as positive if the object rotates with counterclockwise motion, whereas it's negative if the object rotates in clockwise rotation. Now, if the angular velocity of an object changes as it rotates, it's not constant, then it is accelerating and it has an angular acceleration. This is defined similarly to linear acceleration, where we have, instead of the change in linear velocity per unit time, it's the change in angular velocity per unit time. So omega final minus omega initial over the change in time here. And the units of angular acceleration are radians per second squared. Now this image is just showing that, similar to linear acceleration and velocity, the signs of the angular acceleration and angular velocity determine whether the rotation is speeding up for the object or it's slowing down. So if they have the same sign, then the object is speeding up, the rotation is speeding up, but it's slowing down if they have opposite signs. So this example is speeding up counterclockwise. That would be both positive angular velocity, initial angular velocity, and positive acceleration or angular acceleration. Speeding up clockwise would mean both are negative. And then for opposite signs, we can have slowing down clockwise, which is a negative angular velocity and a positive angular acceleration, or slowing down counterclockwise, where the angular velocity is positive, but the angular acceleration is negative. You can see now that for each linear kinematics variable that we have encountered previously, there is an analogous rotational quantity, and this chart shows that. So, for example, for displacement, and the linear quantity was x in 1D, the rotational quantity is theta. The angular velocity is omega and the linear velocity was v. And then we have acceleration, both linear acceleration and angular acceleration. And there are some relationships that relate those here. You won't be required to do quantitative calculations with the angular quantities that I've introduced here, but we will go on to do some calculations involving torque and static equilibrium in the next 2 sections.